inviting me. I'm glad I have the chance to share my results with you concerning the computational characterization of single atom species on metal-supported oxide thin films. Let me first share an idea with you on why are we interested in it. First of all, there's a growing interest on single atom species in the field of heterogeneous catalysis. They are emerging as highly dispersed and highly active metal species. In a way, they are the natural limit of reducing the size of an active metal nanoparticle in catalysis. In this work in particular, we are focusing on three types of atoms: potassium, gold, and platinum. And on the other hand, why are we interested in metal-supported oxide thin films? This is already 20 years long history at least. At first, they were introduced as a model system for oxide surfaces, and their very reduced thickness allowed to employ high-resolution electron microscopy techniques to characterize the surface. But later on, they emerged as a new class of materials with very peculiar properties related to the interplay with the metal substrate. They can be themselves a model of catalyst, the so-called reverse catalyst. And in particular, the most important things that can take place is the charge transfer. It is possible to transfer an electron from the metal substrate to any adsorbate that you put on the oxide thin film surface or vice versa via electron tunneling through the oxide film due to the very small thickness of the film. And the key parameter to characterize this charge transfer phenomena is the work function. The work function is defined, as you can see on the picture, as the energy difference between the Fermi level of the metal and the vacuum level. So depending on the work function, there will be it will be more or less easy to transfer an electron to a substrate adsorbed on the oxide thin films, or vice versa. And computational chemistry, I hope I will be able to prove this point during my talk, is a powerful tool to scan various systems on an equal footage. And in particular, what type of substrates did we explore in this work? Well, we tried to scan all over the most common types of oxide thin films that have been experimentally synthesized and studied, starting from the most paradigmatic one, magnesium oxide monolayers and bilayers supported on silver and molybdenum. Then we moved to this bilayer graphitic-like zinc oxide film supported on the Carnage metals. We then extended the study. Sorry, I have some problems in going on with the presentation. Okay. Then we moved to the silica bilayer supported on platinum and ruthenium, or to a peculiar phase of titania called lepidocrosite. This is a native two-dimensional phase supported on platinum and silver. And later on, we also studied a very thin monolayer of zirconia supported on platinum and on a zirconium-platinum alloy. As I said, all these systems have been experimentally growth and characterized, and we are spanning over very different type of oxides, more ionic versus more covalent ones, non-reducible versus reducible, and so further and so on. And the database that I consider in this work is large enough to take into account many factors. We are dealing with films of various thickness. The strain related to the mismatch with the metal is different from case to case. The type of chemical bond binding the film to the metal is also very different. In some cases, these films are just like weakly coupled by van der Waals forces to the metal substrates, while in others they are strongly bonded. The computational methodology that I adopted is the following. We are using periodic slab models we treat the metal with gradient generalized approximation density functional theory, in particular with the PBE functional. We include long-range dispersion, and in those cases where the d electrons from the oxide display strong correlation, we use an oxide Hubbard parameter to correct. And we started by studying the adsorption of the metal of the single atom, on the freestanding oxide films, and then we moved to the metal-supported films. Here, as I said, a key parameter is the strain related to the fact that we have to adapt the lattice of the oxide to the one of the underlying metal, and these changes in a way the surface chemistry of the oxide film. And then we performed the general comparison in terms of adsorption energy, charge state of the atom, and most favorable adsorption site on all supports. So let me start by examining the main results on MgO. So as I said, we are considering the adsorption of three types of atoms: potassium, gold, and platinum. And in these histograms, I'm reporting the adsorption energy of these species on MgO. And in the case of metal-supported MgO, I'm also reporting with the green histogram the work function of the system. And what happens is the following. If we start from potassium, we can see that potassium on freestanding MgO is only very weakly bound, like 0.3 eV. This is just a van der Waals dispersive interaction. But something happens as soon as we go to silver-supported MgO. Namely, potassium is ionized to potassium plus. An electron is transferred via tunneling effect to the metal substrate. And as you can see, we also have a strong increase in the potassium binding energy. And the larger the work function, the stronger the increase in the adsorption energy of potassium plus. This is due to the fact that large work function implies deeper acceptor states on the metal substrate. The metal is more prone to accept electrons if the work function is large. And here on molybdenum, the work function is much smaller compared to silver-supported MgO, and as a result, we do not have a full ionization of potassium, and the binding energy is only slightly larger compared to the freestanding case. Gold displays in a way the opposite behavior, and the adsorption energy is larger on substrate with small work function. Why? Because gold is much more, of course, electrophilic than potassium. It likes to be stabilized as an anion, as gold minus. And this is easier if the work function of the substrate is smaller. Small work function means shallow donor states in the substrate. It is easy to extract one electron and transfer it to the adsorbate. Platinum is negatively charged on both silver and molybdenum supported MgO, but as you can see, it does not display a very clear trend with respect of the work function, and its binding energy is very strong also on freestanding MgO. Moving to ZNO supported on copper, silver, and gold, we notice that the work function of the system increases when you go down to group. So it is 4.16 EV on ZNO on copper and becomes 4.32 electron volts and 4.96 electron volts on ZNO supported on silver and gold respectively. And potassium is ionized on all supports, also on the freestanding ZNO film, so in absence of any metal substrate. But you can see that, as we can now expect, the adsorption energy of potassium increases as the work function increases, while gold displays, in a way, the opposite behavior. It is not ionized on freestanding ZNO, while it becomes gold minus on metal-supported ZNO, and binding energy is larger where the work function is smaller. Platinum, once again, does not display a clear dependence with respect to the work function. It is worth noting that the trend with respect to the work function doesn't really hold true for the case of ZnO on silver. Here, both platinum and gold are bound in a way more strongly that one could expect based on a work function argument. If we move to silica, we have a case where on the freestanding film, all three atomic species are bound very weakly. And things changing remarkably for the meta-supported silica bilayer. Here the work function is very large for silicon platinum and much smaller for silica on ruthenium. And for this reason, we have a much larger absorption energy for potassium plus on silica on platinum compared to silica on ruthenium. Gold, in the case of SiO2 supported on PT, is still absorbed as a neutral atom, and as you can see, it's very weakly bound. Things changing on ruthenium, where gold becomes gold minus, thanks to the smaller work function of the system. And also platinum is ionized on this SiO2 ruthenium system, but remains neutral on silica supported on platinum. In the case of lepidocroside titania supported on silver and or platinum, well, here the situation is a bit different from the cases where we have seen up to now, because the oxide is pretty much reducible. So we have a possibility to host electrons also on the oxide lattice. And we noticed that in spite of the fact that TiO2PT and TiO2Ag display very similar work function, please look at the green histogram, the ionic bonding of K plus and gold minus display remarkable differences in terms of adsorption energy. In particular, the atoms are more strongly adsorbed in the case of titania on platinum with respect to titania on silver. And this is due to the interplay between the film and the substrate. Titania on platinum has a small charge transfer, while in the case of silver, the titanium dioxide film, even in absence of any adsorbate, is negatively charged. There is some charge spillover from silver to titania. And this in turn influences a lot the formation of ionic adsorbates on the film. And the platinum is very, very strongly bound, as you can see. 4 eV, more than 4 eV on TiO2PT and 3.6 eV on TiO2Ag. This for a single atom is a large absorption energy. This is due to morphological factors. The lepidocroside film is prone to a complex in a very efficient way a single atom due to its peculiar surface profile. Finally, moving to the zirconia tin films. Well, here we have to specify something that was a remarkable finding. Zirconia as a bulk oxide is a known reducible oxide, while it is pretty much more reducible in form of a thin film. And this influences in a way its adsorption properties. For instance, potassium becomes potassium plus, and it is strongly bound on that type of film. And in general, zirconia on platinum seems to be more reactive toward all atomic species compared to zirconia supported on the zirconium platinum alloy. This is due to the large strain that the film undergoes in the ZrO2PT system compared to the ZrPT support. And this makes the film more reactive, and therefore the adsorption energy of all atomic species is larger. And the film is very flexible. When you put platinum on top of it, there is a strong local rearrangement of the film, which permits to bind very strongly the platinum atom, as you can see. The same takes place also on freestanding zirconia. Let me try to summarize. In this plot, I'm reporting the adsorption energy of potassium on all the substrates that I have mentioned and described up to now. and as a function of the work function of the substrate. And this green dashed line is the energy of the 4s orbital of potassium. So what happens if we start increasing the work function of our substrate? It means that an acceptor state gets deeper and deeper in energy until the point that it is at a lower energy compared to the 4s orbital of potassium, and this is more or less where you should expect the charge transfer to take place. Of course, it's a very rough approximation because this is just an initial state. Then during the calculation, the wave function will relax, so the relative energy of the orbitals can change. But as you can see, it sorts of hold true and explain the whole picture. As soon as the work function becomes large enough to make the charge transfer favorable, the binding energy of potassium in form of cation starts to increase. And in spite of the fact that many other factors actually matters, like the thickness of the film, the morphology, and so further and so on, the correlation is really quite good. So in a way, potassium really obeys to a strictly ionic rule of bonding on oxide thin films. And the larger the work function, the larger the absorption energy. What happens if we consider a species which is prone to form anions? We get the opposite trend. The smaller the work function, the larger the absorption energy. Why? Because small work function means shallow donor states. It is easier to transfer an electron via tunneling through the film to the gold adsorbate. As you can see, there's a remarkable outlier here, a silica bilayer on platinum, even though we could expect the charge transfer to take place because the acceptor state is lower in energy compared to, higher in energy compared to the 6s orbital of gold. The charge transfer does not actually take place. We still have spin density on the golden atom that maintains the electron configuration as an isolated atom. As you can see, in general, the trend is worse compared to the case of potassium. So in the case of gold, we have some other factors like a covalent character of the bonding that starts to take place. And this is evident, for instance, in the case of the zinc oxide bilayer on silver or gold. As you can see, we have like a larger absorption energy than we could expect compared to a barely ionic trend. This is due to the fact that the orbitals of silver are pretty much protruding in space. The same holds true up to a certain extent for gold, and this induces a mix-up with the orbitals of gold and stabilizes the bond. If we try to play the same game with platinum, well, nothing works. The correlation is really not existing. Platinum doesn't care about the work function of the substrate because it forms mostly covalent bonds. So it doesn't matter if you have shallow donor state or deep acceptor states. It is more a matter of how much the film adapts to the absorption of platinum to form strong covalent bonds. The only type of sort of way we found to group out the data and derive some trends is represented here on the upper right panel. I'm basically grouping the absorption energy of platinum as a function of the platinum-oxygen distance on the film. And as you can see, one can clearly identify three different groups. The first group here are all the cases where platinum is a bond as a neutral atomic species on the film. And the distance to oxygen is smaller compared to those cases where platinum form a single anion. And in turn, the cases where platinum acquires a -2 charge display a much larger distance to oxygen. This, of course, makes sense if you consider that oxygen is also an electron attractive species. So, of course, you don't want to put an anion too close to it. And as you can also see, we can modulate the charge of the platinum adsorpted atom spanning from 0 to -2, depending on the type of substrate that we are using. And we can even, there are even cases where, for instance, MgO bilayer on silver is -1, or no, sorry, I was no here. Silica bilayer on platinum is neutral adsorption for platinum atom, while silicon bilayer is -1. So we can tune the charge state of the platinum atom by changing the metal substrate underneath the oxide film. Then we explore the further aspect while focusing on the silica bilayer film. This is a porous structure. If you look at the top view here, there are these hexagonal rings, and atomic species may want to permeate through the ring and go at the interface between the film and the metal substrate. And we tried this for platinum atoms on silica bilayer supported on ruthenium or platinum. And as you can see, in both cases, we have a strong increase in the adsorption energy if the platinum species can penetrate through the film and go to the interface. Like in this case, platinum is stabilized here at the bottom layer of the silica film, while on platinum it goes even more down and strictly interact with the platinum substrate. And as you can see, the increase in binding energy is striking. So the adsorption on the, like above the film, is metastable with respect to the platinum atom coordinated on coordinated at the metal oxide interface. But we have to consider that the process of diffusion through the film is an activated process. There will be a kinetic barrier to be overcome due to the penetration of the atom through the oxide film. And we did this for a series of atoms spanning from copper, silver, gold to platinum. And as you can see, we find a remarkable dependency of the diffusion barrier from the metallic radius of the species. The diffusion barrier is small, 0.3 electron volts for a small atom such as copper, while if we increase the metallic radius, we get almost an increase by a factor 2 of the diffusion barrier. So these are the two papers summarizing our main finding. They appeared over the last 2 years on the Journal of Physical Chemistry C and the Journal of Chemical Physics. And just let me throw a few conclusive remarks. As I said, potassium is adsorbed mostly as a potassium plus ion on most of the substrates that we consider, and its adsorption energy is strongly dominated by Coulombic forces, and it is more favorable on supports displaying a large work function. However, there are some significant deviations, implying that other factors may play a role too. For instance, the thickness of the film. The larger the distance of the potassium plus cation from the metal substrate, the larger the charge separation that we apply, and this is penalized by the Coulomb's law. Gold is mostly adsorbed as an anion, as we can expect from our knowledge of general chemistry, but its adsorption energy displays a complicated multi-factor picture. However, there is a general trend of stabilization on supports, displaying shallow donor states, that is, smaller work function. All the relevant factors that I mentioned are the film thickness, the strain of the film, but also peculiarities due to the chemical and morphological properties of the oxide film. In the case of platinum, the bond is strongly covalent, so we see no correlation whatsoever with the work function. An important methodological remark: we did not include up to now any quantum dynamical factor. So we are just doing like a normal density functional calculations and having a look at what is the final state of the wave function in terms of charge state and type of chemical bonds envisaged by all the species that we include in the simulation. but we are not describing the migration of the electron from the atom through the film to the metal substrate or vice versa. Let me mention the source of funding that we got from the Italian Ministry of University and Research, and also the support I had from the Cineca Italian Supercomputing Center for performing this calculation. And of course, thanks to all of you for your kind attention, and to the organizer for giving me this opportunity to share my results.